Hey team, welcome to Level 3, 3.4 Atomic Structure and Bonding, Lesson 6, Part C. Okay, so we just finished last lesson talking about the shape and polarity of these two molecules. This being Level 2, I would expect you to understand, and we have been doing it since Year 11. Okay, so just to recap all of the Level 2 shapes, I will be going through this again when we get to the shapes topic. I'm just doing a little recap now so we can fully understand the polarity aspect. So this is tetrahedral shape where there are 4 electron density regions and they repel as far as possible. These 3 that are on your screen, so this is trigonal planar with 3 electron density regions and this is linear with 2. These are all the parent geometries for Level 2, and what that means is that all the other shapes that you learn are derived from these 3, okay? Because lone pairs, they repel just as much as a bonded pair, and so therefore the lone pairs contribute to the shape. So this here has 4 electron density regions and a bond angle of 109.5. You actually have to memorize these. Everybody does. That's just part of life, okay? Trigonal planar, 3 electron density regions and 120 degrees. And linear, 180 degrees between these two here and 2 electron density regions. So these are the parent geometries which all shapes are derived from. So if there happens to be a lone pair, so for instance here, there's a lone pair, that still counts as an electron density region. So 1, 2, 3, 4, so still 4 electron density regions. They all repel as much as possible, but because this is a lone pair, it doesn't get included in the shape, so that actually changes the shape. And so this is called trigonal pyramid. Okay, so it's based on the tetrahedral parent geometry because there are 4 electron density regions, and that's why it retains the bond angle of 109.5, but now because there are 3 bonding and 1 non-bonding, the shape is trigonal pyramid. Now this here is technically not correct, but I'm not going to go into it now. If you do scholarship with me, I will go through that. For some reason, NCA just stick to these derived from the parent geometry bond angles, but it's not technically correct. Okay, so let's look at this next shape. This is bent. And there are 4 electron density regions still, so it's just that these 2 are now lone pairs, okay? So 4 electron density regions that all repel each other as much as possible, okay? And so the parent geometry is tetrahedral. Apologies, this looks like I've missed off an L there. And so still derived from that bond angle of 109.5. So we're talking about, when we say bond angle, by the way, it's between bonded pairs. I don't know if I specified that before. So there are 2 bonding here and 2 non-bonding. So the non-bonding repel just as much as the bonding, but they don't get included in the shape, and so therefore the shape becomes bent, also known as V-shape, because there are 2 bonding and 2 non-bonding. The last shape here has got 3 electron density regions, which means it is derived from the trigonal planar parent geometry with a bond angle of 120, okay? These lone pairs contribute to, so they repel just like the bonding, but they don't get included in the shape, and therefore 2 bonding and 1 non-bonding, and we describe this as being bent. So what you're going to see here is these are the same. What? Same shape? Yeah, well, they're called the same, but they have different bond angles. So the bond between these 2 here is 109.5, and that's because it's derived from 4 electron density regions. And this bond angle here between these 2 bonded is 120, and that's because it's derived from trigonal planar, and that is very significant. Okay, so those are level 2 shapes, and we'll come back to those a bit later on. If you wanted to do a bit of practice now, because you're like, oh man, that was hard, page 29 to 30 in your SciPad, excellent, answers are on the OneNote. Cool, so we're now back to our 3rd type of intermolecular force, hydrogen bonding. This is the hardest of the 3 to get to grips with, and it's got kind of some niggly wording you have to watch out for. So if a molecule has a covalent bond, so a covalent bond between H and F, N or O, then what happens is that creates a very strong dipole. And the reason why it creates a very strong dipole is because these 3 are the most electronegative atoms that there are. And so they're going to pull those electrons in that bond much closer towards themselves than the H atom. So that makes the H super positive, okay, delta positive H, and it makes the other element super negative, so such as fluorine. So the electrons sit way closer towards the fluorine. So first of all, that's the first criteria for a hydrogen bond, and that's that the molecule itself must contain a covalent bond of an H to F or H to N or H2O. So a really common example that you've seen your whole lives, and we've even done the Lewis structure just before, is going to be water. Okay, so it's got this OH covalent bond. O is far more electronegative than H. It's one of these special three. So this oxygen becomes negative and this hydrogen becomes super positive. And because we know how to do shapes now, I'm just going to draw it like so. So the oxygen's super negative and the hydrogens are super positive. I kind of get kids to think about it like a super dipole. Okay, so that's the first criteria, that there has to be this covalent bond. And then what happens from here is, because this hydrogen is super positive, it's going to attract a neighboring water super, super strongly, okay, because the dipoles are so strong. So this is the H bond. It is still an intermolecular force, but it's just that it is a super strong intermolecular force, okay, between the super dipoles that are created because of these covalent bonds. Okay, so hopefully that's made sense. So here's that picture of water. Again, there has to be this covalent bond so the strong dipole can be created, and that means that that super positive hydrogen will attract the super negative oxygen extremely strongly, creating the H bond intermolecular force. Again, NH3, okay, so N's one of those three atoms, so the atoms, as a refresher, were F, N, and O, okay, must be this covalent bond. It makes the nitrogen super negative, the hydrogen super positive, so it's going to attract to a super negative of a neighboring molecule, and this is the H bond. So the H bond is the intermolecular force, but for this H bond to exist, there must be this covalent bond present. Okay, so can H bonds form between two different molecules? And the answer is yes. Okay, so here we've got water. Okay, you've got a negative oxygen here, and it'll attract to the positive hydrogen of a neighboring molecule here. So perfectly fine. Both of them have got this covalent bond. So H bonding in liquid water. So this is just to show you. So here's liquid water. You've got water molecules attracting just as we saw before. Interestingly, this is what the H bonding looks like in solid water, ice. And if you look here, you can see each water molecule is attracted to another water molecule, and it's in 3D, and you can see that it forms these like hexagon shapes with massive gaps in the middle. And that's because water actually has multiple sites that it can form hydrogen bonds, because each water's got a hydrogen that can bond to an oxygen, and there are two hydrogens. So this hydrogen can bond to this oxygen, this hydrogen can bond to this oxygen. And what you'll realize is that on the oxygen, there are two lone pairs. So those lone pairs can also provide a spot where they can then H bond to a hydrogen of neighboring molecules. So because of that, each water can actually make 4 hydrogen bonds to other waters. And when they start moving slower, which they do at cold temperatures, they get themselves into this totally stable configuration where they're all maximizing the H bonds. And when they do that, they form these hexagonal rings. And what you'll notice is there's a massive gap in the middle here, and a massive gap here, and a massive gap here. And that's actually why when you freeze water, it expands, and that's because the structure that they're taking up has lots of air pockets in them, or vacant space, I should say, vacant space in them, and that makes them larger, and that's why they're actually less dense, because there are less particles contained in a given space. So isn't that interesting? So that's what water does there. Okay, so here's a quick question. I saw this as in an NCA exam one point or sometime, and I was like, oh, great question. So does this exhibit H bonding? And the answer is, hopefully you're yelling it out to me, no. Okay, it trips up students because there are H's and F's in it, but it's not the H bonded to the F, and therefore it does not exhibit hydrogen bonding. However, we can actually discuss quickly the types of intermolecular forces it will have. Because it's a molecule, it'll have temp, because all molecules have temporary dipoles, because they've all got electrons moving around, which can cause a positive side and a negative side. And second of all, it's polar because of this F not being the same as this H. And so therefore the dipoles do not cancel. So it'll also have permanent dipoles, but it won't have H bonding. So hydrogen bonding have the most influence, then permanent and then temporary dipoles. And that's there's actually, it's hard when you say this, so you just have to realize that they are the strongest if you're comparing very similar sized structures. And we're going to get to a point where you'll see where this doesn't actually always hold true. But a good thing to know is that hydrogen bonding has the most influence, then permanent and then temporary. So a bit of a summary. Okay, bonding between a molecule will affect its physical properties. So that's what we've been talking about here, so melting point and boiling point. And the larger your molar mass, the larger the electron cloud and the stronger the temporary dipoles. Or if it's a straight chain molecule, it'll pack together much closer because there's greater surface area and the temporary dipoles will be stronger. For H bonding, there must be one of these 3 bonds between them, inside them, and then they can attract to neighbouring molecules. And H bonds are stronger than permanent dipoles, which exist in all polar molecules. So here's a wee task. I'd love you to pause right now and please tell me, what type of bonding do the following have? You might have to draw some Lewis structures to work out if structures are polar or not. These are all just straightforward Lewis structures from level 2. Here are my answers. Okay. This first one here, CH4, is just standard CH4. It's non-polar, so temporary dipoles. Second one here is polar, okay, because of this here. So it'll have permanent dipoles, and temporary dipoles. Sorry, that should say and temporary dipoles. This next one here, CuCl2, is ionic. Don't get tripped up. They love throwing this into NZQA exams just to throw you. So metal and non-metal makes ionic. This next one here, I've drawn it out for you here because there's a lone pair. It's going to make it polar, and it contains this NH covalent bond, which means it's got H bonding. And remember, every molecule has temporary dipoles. Cu, if you ever see just a metallic metal element on its own, that just means that it's metallic, okay? NH3, if you draw it out, okay, from level 2, there's a lone pair that makes it polar, okay, so it'll have temporary, permanent, and it's also got this NH, so it'll have H bonding. FeO, metal and non-metal, ionic, don't fall for the trap. Okay, ethanol looks like this, okay, and so you can see here lone pairs that make it polar. It'll have temporary because all molecules do, and there's an OH covalent bond, so it'll have H bonding. This next one here is just non-polar, so it's just temporary. Water, okay, lone pairs that make it polar. It's got the OH, so it'll also have H bonding, and because it's a molecule, it'll have temporary because it's got electrons. NaCl, ionic, metal and non-metal, and Mg's metallic. So hopefully that went well. Any questions, see me. Apologies about this, that should have temp, and I'll add that to your OneNote slide. Okay, task 2, so account for the difference in boiling point of these two structures. Let's quickly go through the answer. So these are actually isomers of each other, which means that they've got the same molecular formula, which is C5H12O, okay, C5H12O. So they've got the same molar mass and the same sized electron cloud. So we would expect these two structures to have the same strength temporary dipoles. But what we can see here is that one's got a massively higher melting point than the other. So something else has to be having an effect here. They both have an OH group. By the way, that's shocking bonding. If you did that in organic, you'd get told off. C to OH, I always put that there to discuss those. They're all over the internet, terrible bonding. So they've both got the OH, making both structures polar. So they both have permanent dipoles. And because they've both got the same OH, then they'll both have the same H bonding too. So they've got the same permanent dipoles, the same hydrogen bonding, and they've got the same sized molar mass, so the same sized electron cloud. So why is this one way higher? And it's because this structure is a straight chain molecule, which means that they can pack together more closely. There's a greater surface area between the molecules, and the temporary dipoles will be stronger, so more energy to break. I've written this out neatly here, so you can pause and have a wee read and get back to me if you have any questions. Cool, we've finished the lesson. Well done, team.